Okay, hi. I'm Sramana, and I'm presenting some work that I've been doing as part of my postdoc with Julia Bluster and Christian Jacob at Monash University. And we're looking at, so basically, we've heard a lot about the need for high-resolution global climate simulations already from the morning, and also the roadblocks that we have in place. That's hindering this development of high-resolution simulations. One major roadblock that we all know is computational resources, not just the computational simulation time or simulation resources, but also storage for the huge amount of data that these high-resolution simulations produce. So our aim is to see if global climate model simulations can be run for short time periods, typically a few months or a season, with reasonable confidence in the model errors. We want to see if, so basically our approach is to run a simulation for a few months, say 3 to 4 months, in a global climate model. And as a first step, we have tried to estimate how much we can learn about the climatology in this global climate model from an atmospheric simulation in the AMIP configuration from shorter samples. So we basically create very random short samples from the whole climatology of, say, 35 years in the ACCESS-CM2 model in the AMIP configuration. And we analyze the errors of these, analyze the climatology in these samples and see how close we can get to the climatology of the whole global model simulation. We've used the ACCESS-CM2 model in AMIP configuration. We're still concentrating on the low-resolution N96 model, and we've only used one ensemble member in this work. We've basically tried to evaluate if the mean model errors of in this model, in the AMIP simulations, can be reproduced in these short samples, in our short samples, and trying to quantify how many short samples we need to reproduce the climatology. So, if you look at a random 1-year sample of the from the AMIP simulation and compare it to your 35-year climatology for, say, surface precipitation here, you already see that certain spatial features are, general spatial features are already pretty well captured, even in a 1-year simulation. And we want to see if we can sort of see how many short samples would be enough in this case. So if you compare the deviation from the climatology in that 1-year sample, you see that there are some certain deviations in the spatial pattern around in certain regions. But if you use a 5-year sample, those deviations almost disappear. So a 5-year sample seems pretty close, seems to generate a pretty close approximation to the climatological patterns. Similarly, if you compare the errors that are that you see with observations in these short samples with the climatological errors with observation, we've used GPCP here. Again, with a 5-year sample, the deviations all but disappear again. So we want to quantify how many short samples are enough in this case. And so for that quantification, this does not come up well. These are actually box plots to show the variation of errors in each sample. So we basically have selected short samples from the 35-year simulation in the combinations of 1 to 35 years. So you have a 1-year sample, a 2-year sample, till you go to a 35-year climatology. And these are randomly selected multiple times, so in order to reduce the noise from these samples. And we've compared the root mean square error for temperature and precipitation. I'm sorry, this plot doesn't show up, I don't know why, but the red lines are for temperature and the blue lines are for surface precipitation here. And we see that if we look at the root mean square error for a season, for DJF, the errors start decreasing with increasing sample numbers. So the x-axis is different sample numbers or different years in the samples. And that is to be expected, right? Like if you have an increasing number of samples, the errors will decrease. But what is interesting is if you look at the deviation of these errors with the 35-year climatology, you see that that is what is defined as relative error here, that is the deviation of each of these errors in the samples from the climatology as a fractional deviation, right? So you see that as we go down with increasing sample numbers, that relative error also decreases. But interestingly, if you're interested in a 10% error and in temperature, you can expect, say, a 3-year sample to give you enough confidence in the climatology, and you can get away with a 3-sample simulation for that season. So we wanted to quantify this further, and I'm so sorry, I don't know why the plots are not showing up, but basically this is a summary figure where I've compared the minimum number of samples that you need for different variables, taking the median from each of these samples. And I've compared them for a particular relative error threshold. And the black line here is basically the mean over all the variables. And we can see that if you are comfortable with a 10% error, you can get away with a 3-member sample. Yeah, a 3-member sample seems enough to capture the climatology in this case. So we also wanted to reproduce this in short simulations using the ACCESS model. So we've used the ACCESS model in an AMIP configuration, and we've tried to run these short simulations where we basically run the model for 1 year, a randomly selected year, and then we use the restart files for each generated for each month as our initialization condition for short simulations. So for example, if you run August, September, October, November simulation, you use the restart file for August as your initialization condition, and then you run the model for 4 months. And we've created a collection of 36 members using 4 years of simulation for different SST conditions, and then and different initialization conditions from the 1-year runs. And I'll quickly go through this. So this is just to show that the climatology, the definition of climatology for our short simulations work well when comparing with the existing AMIP simulations for ACCESS. And if you also have, also compare this with a random 4-member sample for the short simulations, you see that again the spatial patterns are pretty well captured. And just quickly to show that, I'll skip through this slide for interest of time. And quickly, just to show the summary figure, where again, this was showing the mean over some variables, but if you are interested in a 10% error again, a 4-member sample seems enough. Just to point out that our short simulations are not just years, it has different initialization conditions as well. So we do not need, you don't need to run a 4-month simulation for, say, 4 years. It can be different initialization conditions as well to get similar results. Yeah, thank you.
Thanks, Sramana. Do we have any questions? Yep, Ed.
Thanks, great talk. Does the number of samples you need change depending on the spatial area that you want to average this over?
More or less, but not too drastically. So we've also compared this for tropical regions, but all of the simulations I showed were global means. But if you also look at tropical areas, it's around 6 members to 7 members is enough. So it's not a lot of difference, a little bit.
The same question. I want to know for model resolution, if you had a high resolution model, we end up with the same sensitivity.
That's the next step. You need, that's like, so all of this is with N96, but we have to repeat this with a high resolution simulation.
What's your guess?
Sorry?
What's your guess?
I think it would, we would need a little more members, but I hope not. The whole point is to look at the mean climatological errors in this case. If we can reproduce the mean climatology in higher simulations for these short runs, that's the whole point. So of course, if you're looking at extremes or certain weather patterns or certain weather phenomena, you will need more members, but the mean climatology, I guess, would be reproduced even in the higher resolution simulations.